Okay, so now I'm going to tell you how to set up the scale-invariant trait-based model. Now, from a coding perspective, this is very, very similar to the trait-based model. You can think of it as a type of modified version of a trait-based model. Mathematically, I think it's a bit nicer. It has this kind of scale-invariant property that the system looks sort of similar at different size scales, and basically this system has a lot of nice symmetries which allow us to be able to specify its steady state. And this has various advantages in the sense that if you look very carefully at some of the other models, for example, the trait-based model in Mizer, you'll see that it's basically very reliant upon having a often rather strong stock recruitment relationship, which is kind of added into the system and basically means that lots of the eggs which are being produced are actually not being accounted for. They're being sort of lost. And this, if you're not careful, can introduce sort of artificial stability into the system. Whereas for this scale-invariant trait-based model, we're able to actually do away with such things and really let the system do what it wants to. Now, the basic way we set up such a thing is with this set scaling model command. So in a similar way to the trait-based model, we have to tell Mizer various things. So we set the number of species as 10, the minimum asymptotic size is 10, the maximum asymptotic size is 1,000 grams, the minimum. But one of the differences in this model is that the egg sizes can actually be different. I'll talk about that later. Let me finish describing the inputs. So here, the minimum egg size is 10 to the minus 4 grams, and the minimum maturity weight is 10 to the power of 0.4. That's about 2.5. And the value of kappa that specifies the sort of overall abundance of the community here, we'll set it to be 0.005. So let me just run that command. Yes, now let me talk about the thing about the egg sizes. So there is quite some evidence that lots of fish have eggs at the same size. However, for other marine organisms, there's evidence that the egg size actually sort of varies with the asymptotic size of the organism. And nevertheless, in this scale-invariant trait-based model, we assume that these fish have egg sizes proportional to their asymptotic size, and that there's a lot of mathematical advantages to doing that. It basically allows us to specify a steady state and have it really remain steady without having to introduce any kind of stock recruitment relationships, which are done in other models and basically correspond to eggs being lost from the system, not always with with good reason, I would say. Anyhow, this basically makes us a params object. Now it's a little bit richer than some of the params objects previously in that it has some rather informative slots to it. So if we do params at initial end, this is one of the slots, and what this actually is, I'll just press return, it won't probably mean much to you, but it's actually a specification of the abundances of the different 10 species here at the steady state, or very near to a steady state. So this model has the advantage that we can basically get a mathematical formula for the steady state, and we've already fed that into Mizer so that it automatically starts our simulations off close to the steady state. Well, maybe I shouldn't say the steady state. A steady state would be more accurate. We haven't we haven't proved that this is the only steady state of a system. Anyhow, we have this Mizer params object for our scale invariance model, and we can run a simulation on it using the usual command and make plots of the results. So you see here, hang on, let me just let it load. Okay, you see here that in this biomass, in time versus biomass plot, the biomasses of the different species are basically staying constant all along. That's because, well, almost constant, a slight change at the beginning, but basically we've started very, very close to a steady state of this system. And the nice thing is we can have the system at this steady state, and in most cases it's stable there, so small deviations away from it. If you have a small deviation away from this and you evolve the system, it will get attracted back to the steady state. So it's going to be a stable steady state usually, without having to include any stock recruitment relationships. And also we can see here from this plot of the biomass density at different weights that the system has a lot of symmetry to it. That's really the essence of this scale invariant notion, that there's a sort of symmetry to the system over different size scales. So if we do this plot spectra command here, we can see that biomass density plot more carefully. And I've also plotted the total biomass density of all of these different individuals. And you can see that that's, because this is a log-log plot, that's very closely following this sort of power law, this sort of Sheldon spectrum, which is often observed in marine ecosystems. And it's really by exploiting the kind of nice properties that come from that we're able to find an analytic solution for a steady state of this system. And basically one can use the scale invariance model as a sort of background or substrate into which one can introduce more species explicitly, say cod or hake or whatever, and one can model them in a sort of way that doesn't require strong stock recruitment relationships. That's in contrast to some of the approaches described before the scale invariant model within the Mizer vignettes, where often a fairly strong stock recruitment relationship is required in order to stabilize the system.